All right, this is a review of the content that is on exam 3 for Physics 221. And where we're going to start is, for this exam, is if you have a plane of charge. If you remember that. If you remember, a plane of charge has an electric field that is uniform. In other words, if it's an infinite plane of charge, the strength of the electric field is the same no matter where you are. And to the right of the plane, it goes that direction, and to the left of the plane, it's in the opposite direction. And the strength of the electric field, the direction is given by, in this case, to the right or to the left, because the plane's vertical. But the strength of the electric field is given by the charge density, which is in coulombs per meter squared, divided by 2 epsilon 0, if you remember that. And epsilon 0 is the constant called the permittivity of free space. It's 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared. And so that was something we talked about. And of course, if the charge were positive, these lines would be directed away from it. If the charge were negative, then the lines would be directed towards it rather than away from it, but it would still be a uniform electric field associated with the negative plane of charge. Draw that a little bit more cleanly. Something like this. There we go. Okay, so positive charge, electric field away, negative charge, electric field towards. But the strength of the electric field in both cases is given by that equation for a single plane of charge. And of course what that means is if you put a charge here, if you happen to set a charge somewhere in space near that electric field, the charge would experience a force on the charge equal to the size of the charge times the strength of the electric field. That's how big the force would be. And the direction of the force would be, if it were a positive charge, it would be in the direction of the electric field. For a negative charge, it would be opposite to the direction of the electric field. Okay, so that's what happens when you put a charge in an electric field. And we've talked about that, but that is a concept I want to make sure you still know. Now, what if you put two planes close together? You have a plane here and another plane here. And they're opposite charge. That's the only kind I've been talking about, is if you have these planes, but one is positive charge and one is negative charge. Same size charge, just opposite sign. In that case, the electric field outside the planes of charge is going to be 0, way out, all the way over here and all the way over here. It's in between the planes of charge. The electric field goes from the positive plane to the negative plane, and the two effects superimpose inside the field, so it's going to be twice as strong as this inside between the two plates. It's going to be, the strength of the electric field is going to be equal to 2 times sigma over 2 epsilon 0, which is equal to sigma over epsilon 0. That's the electric field strength in between the two planes of charge of opposite sign. All right, so the other thing we talked about is the relationship between the potential and the electric field. We said the potential is equal to, when you have a uniform electric field, it's simply equal to the electric field times the distance. So when you have two planes of charge here, if you know the distance between them, d, the potential, and you assume that the potential of the negative charged plane is 0, then the potential of the positively charged plane is the strength of the electric field times the distance between the two planes of charge. Okay, so that is potential and electric field, how they relate to each other. For two planes of charge. And then we took those concepts and we talked about the fact that, okay, if you have one plane of charge here and another plane of charge here, you actually have some positive charge on here and some negative charge on this one. And this is really a way to store charge. This actually is a parallel plate capacitor. We came up with the equation for that. And if you remember, the equation for a parallel plate capacitor was equal to, if we did the math, we use this equation, which hopefully you remember quite well, Q equals CV. I call it Chula Vista. We have that, if we solve this for C and use our expression for V here and for Q, knowing that sigma is Q over epsilon 0, then we get an expression for the capacitance between the plates that's equal to epsilon 0 times the area of the plates divided by the spacing between the plates. That's for a parallel plate capacitor, where each plate has an area A and they're separated by a distance d from each other. And then, of course, if we put something in there in between the plates called a dielectric, what happens is the dielectric is this material right here. And what it does is the molecules of that material will line themselves up such that the positive ones are close to the negative side of the plate, or to the negative plate, and the negative ones are realigned on the molecules switch to the positive side of the plate. They don't move around. The molecules themselves stay put, but they can flip. And the amount that they flip corresponds to how much of a dielectric it is. Bigger flips mean more dielectric, greater dielectric constant is what we call it, which increases the capacitance. It allows the plates of the capacitor to store more charge for a given voltage. And that, therefore, increases the capacitance. So we come up with an expression for capacitance that's given by this dielectric constant, which I called kappa here, times epsilon 0 times A divided by D. That's the dielectric constant. The rest of the equation is the same. But it's a way to increase the capacitance of a capacitor. Then we talked about, we did some example problems where you had a capacitor, and if you knew what its capacitance was, and you wanted to determine the amount of charge on the capacitor, where we kept coming back to this equation, Q equals CV. And so if you knew what the capacitance of the capacitor was, and you knew what voltage it had across it, then you could determine the charge on it. So given that you know two of these, you can always find the third. Then we talked about parallel and series capacitances. We came up with the idea that I derived for you, actually, that if you put two capacitors, C1 and C2, in parallel, that the equivalent capacitance is simply the sum of the two. And that both of these capacitors are going to have the same voltage drop across them because they're in parallel. V1 has to be equal to V2. Similarly, if you have two capacitors in series, the equivalent capacitance is going to be 1 over the sum of the inverse of each one. Kind of like parallel resistors. And for these, we realized that the charge on each one has to be the same. The voltage is going to be different, but this one's going to have a different charge on it. I'm sorry, the same charge on it that this one will have. They have to be, because this island here has to have the same, has to be neutral. So whatever's positive here has to be negative here, therefore has to be positive here, and then negative there in the same amount. And we came up with different ways we could find the equivalent capacitance of a network by combining them in series and parallel appropriately. And I gave a bunch of examples of finding the voltage drop across these corresponding capacitors and the charge on those capacitors as well. We also did RC circuits. So an RC circuit is when you have a capacitor and a resistor, and you have some initial voltage across the capacitor. Call it V initial, and this is C and this is R. And what's actually happening is these charges are draining out from the capacitor plate so that they're going to the other plate and the whole thing is going to become neutral. So what we see, and I derived this for you, is that the voltage across the capacitor decays exponentially with time, like that. It starts off at the initial voltage and it goes down basically to zero eventually, or quite close to it. And we also talked about the fact that the product of R times C is seconds, has units of seconds. And that after one time constant, or after a time equal to R times C, the voltage across the capacitor is equal to about 37% of what it was initially, or 36.8%, something like that. All right, so that we derived that, and that's why this time constant is such a useful equation. It gives us a really quick way to determine how long it's going to take for the capacitor to get down to 37% of its original voltage. Then the last concept we talked about was the magnetic field, which is different from the electric field, but it's related. Magnetic field, if you have a current passing through a wire, you're actually creating a magnetic field, and we talked about the fact that the current's to the right, you stick your thumb in the direction of the current, and your fingers are going to wrap around the wire, meaning that the magnetic field is going to be stronger. Is going to be coming out at you above the wire and going into the page or into the screen below the wire. And it's going to get weaker as you get away from the wire. Of course, it dies down as the inverse of the distance from the wire, R. As you get further away, it gets weaker and weaker, as indicated by having fewer of these circles. And inside, if you wanted to get a stronger magnetic field, and I gave you an equation for the magnetic field, it's equal to mu 0, which is called the permeability of free space, times I divided by 2 pi r. That's the strength of the magnetic field. And I guess I should make this capital R to make it consistent with this capital R up there. It refers to the distance away from the wire. If you want to get an even stronger magnetic field, we created what we call a solenoid, which is winding all this wire many turns, and the magnetic field inside the solenoid is uniform. So it doesn't matter where you are inside the solenoid, the magnetic field is going to have the same strength. That's not the case here, notice. As you get further from the wire, the magnetic field is going to get weaker. But anywhere inside the solenoid, it's going to be the same strength. And that strength is going to be equal to mu 0 times n times I, where n is the number of turns per meter. And I should say that mu 0 is, as I mentioned, it's the permeability of free space. It's 4 pi times 10 to the minus 7th. Tesla meters per amp is the unit of it. Okay, so that's our mu 0. And then we talked about what happens if you have a magnetic field, which I'll draw like this. It's pointed in a given direction. And you have a charge that's just sitting there. And if you have a magnetic field and a charge just sitting there, nothing's going to happen. If you have a magnetic field and a charge moving, for instance, in that direction or that direction, nothing happens as far as force is acting on the charge. However, if you have a magnetic field and you have the charge moving, let's say the charge is directed into the board or into the screen. Now, because the charge is perpendicular, since this charge's motion is perpendicular to the direction of the magnetic field, you can use the right-hand rule to determine the force the charge is going to experience. You do this by putting your fingers in the direction that the charge is pointed. In this case, it's coming out at you, actually. It's coming out at you, but the magnetic field is bending to the right, so you stick your right hand and have your fingers pointed at you, just like this dot is. Then bend them to the right. Your thumb points up. That's the direction of the force that a positive charge is going to feel. It's going to be up, in this case. So that's something called basically Lorenz's law. It tells you the direction of force that a charge experiences in a magnetic field. And then the last two topics are incredibly interesting, actually. One of them is Lenz's law. Lenz's law basically says that when you have a changing magnetic field, and a changing magnetic field could be as simple as dropping a magnet through a copper tube or through something. And if you have it near a metal, something that's conductive. So I'll draw conductive here with gray. What actually happens is inside the metal, currents are created, and those currents create their own magnetic field. So these currents that are generated within the metal create their own magnetic field, and that magnetic field opposes whatever's happening. And I have a really nice video demonstration of it on iLearn. It's called Demonstrations of Lenz's Law and Faraday's Law, where I drop a magnet through a copper tube, and you see the magnet go really slowly through the copper tube. In other words, gravity would want to accelerate it, but as it's moving, the currents that are generated inside the copper tube, if they could talk, they'd say, we don't like this change happening. We want this change to stop. We want to slow it down. So they're going to slow down the magnet's fall. They can't stop the magnet's fall, because if they did, then there wouldn't be anything to change. So they slow it down, but they don't stop it. And that's Lenz's law. But one of the key things about Lenz's law is it basically says that currents are generated by a changing magnetic field. So it basically says currents are created by a changing, this should be a changing, they create a magnetic field, but the currents themselves were created by another magnetic field. And those currents are trying to oppose the changing magnetic field. I should say they're created by an original changing magnetic field, like a falling magnet. If the magnet were just sitting there, this wouldn't happen. So you have to have a magnetic field that's changing. So if you drop a magnet through a tube, that would happen. If you're able to increase or decrease the strength of a magnetic field by making a battery weaker or stronger, that would happen too. So this is what is associated with Lenz's law. Similar to Lenz's law is you have Faraday's law. Faraday's law basically says these currents that are generated by a changing magnetic field are also associated with a voltage. So by changing magnetic field, you're creating a voltage. So what's true about Faraday's law is if I have a magnet in a loop, and I have another demo of this on the iLearn site, if I have a magnet and you have a loop of wire right here, and I move the magnet in and out of the wire, I'm going to generate a changing current in the wire. It's going to go back and forth and back and forth and back and forth. And that's how we get our power that's generated, which is why it's AC. It's because it's generated by a changing magnetic field, effectively a magnet moving back and forth in a coil of wire. Maybe it's moving back and forth because it's being spun by a wind turbine. Maybe it's moving back and forth because water is flowing past it quickly. Maybe it's moving back and forth because steam that was created by burning coal or natural gas or nuclear fuel is causing something to spin. That is creating a change in a magnetic field, which is then turned into energy that we are using. That's how we generate our energy. So this is an incredibly important concept. That's Faraday's law. Basically says that a changing magnetic field, however you change it, I asked in the videos, you'll see me use the word flux. Flux represents the product of the magnetic field in the area. It's really when the flux is changing that you get voltage or current generated. But changing a magnetic field will certainly change the flux. If you have this loop of wire here and you decide to stretch it and shrink it and you keep the magnet stationary, that will also change the flux, and you'll also be able to generate some energy from that some current from that could be used to light a light bulb or do something like that. And what's interesting, of course, is as this changes, as this jiggles back and forth here, let's say this magnet jiggles back and forth, that creates a changing current, which creates its own changing magnetic field. And that changing magnetic field, one of the last things I will mention in class, or did mention in class, is that a changing magnetic field creates a changing electric field. which in turn creates a changing magnetic field. Which in turn, I could keep going here, you're probably getting the idea, creates a changing electric field, etc. This keeps happening, and we have light. Light is an electromagnetic field created by changing magnetic fields that create changing electric fields or create changing magnetic fields, and that effect propagates away at the speed of light. And we have come back full circle to where we started this semester when we started talking about light. It's all tied together. All right, I hope this helps you as you study for exam 3.